they're not like equivalent, like, because we get this like, yeah, we have this division over 0, and like, what do we do when we have division over 0? Like, we think, okay, if we have a graph and we have this 1 over x and x, and we just replace that with like a 1 over 0, then you can kind of think of that function is going to head off towards infinity, right? Because like, if we had 1 over like 0.0001, that's like, what is that? That's like a 10,000 or something like that. So you can see if we had like 1 over like 0, then it would kind of approach infinity. Like, we can't really say exactly what happens when we have division over 0, and that's a big chunk of math, is figuring out what happens. But that's, yeah, that kind of gives you a little bit of the intuition behind why we went through why we went through all this work to cancel out this delta x, because that delta x is important, but at the same time, like, as you can see, we're going to get this division over 0 unless we can figure out a way to cancel it out. So yeah, so that's just yeah, that's basically I think, so that justifies kind of why we went through all the work to cancel that delta x out. But the key part, remember, was just expanding that that delta x plus x squared. It was expanding this guy and then canceling it, so that we could then we could factor it out, because then we wouldn't have, we have an expression that we could factor out. And so now we're basically done with the problem, or a good portion of it, because the problem originally was we have this function f of x equaling x squared minus 7, and it's supposed to be tangent, well, we need a line that's tangent to this function and is also parallel to this one. So we really solve this last half, this parallel to this y equals negative 2x, because now what we have is we have this function that we were talking about previously, and you can really see then you can really see how this line that we drew here and this line how we drew here, how that really corresponds to this function 2x, because you can see, like, okay, hey, we have this line 2x, what's y equals 2x? Well, it's just this straight line that goes up like that, and you can see that we have this straight line that goes up like that, and we have this straight line that goes up like that, and we just kind of looked over here and we're like, okay, so imagining we're putting this f prime of x, and this is really the same thing, f prime of x right here as well, and we're just thinking about, okay, so then what happens, we really want to find the x that corresponds to this negative 2, because that's going to be where the slope of this parabola is equal to negative 2. So that means all we have to do, and we'd already set up the mathematical expression or the algebraic expression, this f prime of x equals negative 2, and now we have, so that means we'll just plug in that negative 2 right here, and we're just going to be like, okay, so now we have this expression, we have this 2x equals negative 2, so 2x equals negative 2, and we just solve for x, so divide by 2, we have x equals negative 1. So it looks like my first guess at negative 3 is really far off, so sorry about that. But so it looks like at x equals negative 1, then we should have a slope of negative 2, and we could plug that back into our f prime function, f of prime of negative 1. I mean, we just solve for it, but this kind of helps to solidify things. So you can see that, according to our derivative function, and then we have this slope of negative 2, and that should be, and so that means that, like, okay, so at x equals negative 1, so at x equals that negative 1, let me draw another parabola. So we'll just, hopefully this parabola will look a bit better. So let's see here, so this is going to be our negative 7 again. So it looks something like that. That wasn't a very good parabola, but oh well. Okay, so that's not a very good parabola, but it'll have to do. Yeah, anyways. So we're going to pick a point like negative 1, and this is not going to be to scale at all. So negative 1, so that means we're going to have a slope of something like this. Actually, let me try to redraw this guy, because that doesn't look very good. And it's important to have nice looking graphs if you want to get intuition behind things. So that's a bit better. Actually, that looks more like that. Okay, so now at -1 we have a slope. We should have a slope that looks more like this. That's obviously not the case. I'm not an artist here. Didn't go to an art school. Anyways, so we have a -1, and that should be a slope of -2. And this is really the line that we're looking to find. We know at -1 this slope is -2, so m equals -2. So that means we have basically half of our expression of y equals mx plus b, right? Because now we have, this is the line that we're trying to go parallel to. That's why things aren't working right, because I didn't draw this to scale, right? So I was seeing this line is like, never mind. It's like, well, it's like this line was not looking like a -2 slope. I'm used to a -2 slope of looking fairly steep, but since I made this x like much larger than my y's, then that graph kind of gets smushed, which means that this very steep line is actually less steep because I squished up my y's. But anyways, the important thing though is that we know that at x equals -1, our slope is this -2. So that means that -2, then we could plug right into this equation for y equals mx plus b. So that means we have y equals -2 x plus b. And so then yeah. So then we know and we actually, I mean, like, since we had to have a line that was parallel to this y equals, I just realized this, so we had to have a line that was parallel to y equals -2x. We could have just looked at this and been like, okay, we need a slope of -2, so what we can come up with, so m must equal -2, whatever the case. But using this derivative, then we were able to calculate at which x it was equal to, that slope was equal to -2, because the important thing then is we can use this x back in our original function, our f of x function, because that'll give us our y-intercept, our b term. So then we can just be like, okay, so what's the like what point along the y-axis, because we need to place this parallel line, right? Because we have this parallel line, it could be like anywhere while it's in this form right here, because b could be anything, we don't know what it is. So we'll just plug in this x equals -1 right into here, -1. That's going to be, well, our function was f of x equals x squared minus 7. So we can plug in this -1 squared minus 7. And so that's just simply 1 minus 7, which equals -6. So that means we have this f of x equals this -6. And so we know that this point right here is -6. And that looks about right. Which is always nice when the graph looks like it, as it should. So we have this -6, and and so that means what we know is we have a certain x. We have this x equals 1 right here, and we have a certain y that corresponds to it. So that means we could just we have the x and the y to solve for b. So we could just plug in this -2 times our -1 that we're just getting from right there, because that's right where the slope equals -2 on this parabola. And then we have that set to -6, and we just solve for b. And so this is simply 2 is -6 plus b. So that means we just subtract 2 from both sides. We come out with -8 equals b. Just like that. And so that means we have our y equals -2x minus 8. And that should be it. You can graph that on your graphing calculator and make sure that that it's tangent. So it's like touching at a single point this parabola. And you should find that it works. And if this isn't a technique that you know, like taking the derivative, then just call me and tell me what technique you do know, and hopefully I'll have learned that technique too, and I could help you with that. But yeah, hopefully this helps.